Okay, I guess I'll get started. Hopefully a few more people come in. So we are, let's see, we're starting week 2 checkouts for lab 2 this week, which means the Monday sections will start working on lab 3 in 1 week, which means now's a pretty good time for me to start introducing lab 3. I know for a lot of you, it seems like we're still in the depths of lab 2, which we are, but I feel like I should start talking a little bit about lab 3. So I'm going to do that today. The thing about lab 3 is lab 3 is not like the other labs, because lab 3 is about the Mandelbrot set. And the Mandelbrot set is so interesting and so lovely that I can't in good conscience just present a set of equations and then talk about how to implement them. I don't think that would be doing a proper service to the Mandelbrot set. It's too fascinating. And the story behind it is too interesting. So this lecture is going to be different than all of the previous ones in that I am not really going to talk at all about implementation of these equations on the FPGA. My only goal for today is to attempt to explain what the Mandelbrot set is and why it's interesting. And then in the next lecture, we'll talk about how to implement it and get back into sort of normal FPGA stuff. But I feel like this particular mathematical structure deserves this kind of attention. So I want to give it the attention that it deserves. And to the extent that I am able, the way that I want to try to introduce this thing is by attempting to follow the train of thought that Benoit Mandelbrot and other folks followed in order to discover and then subsequently explore and attempt to understand what this thing is. So I'm going to try to do that to the best that I can. And the place to start with this train of thought is in thinking about iterations. And specifically, I want to start thinking about the stability and instability of iterations. So in order to sort of make it clear what I'm talking about, I want to start with a very simple example of an iteration. So let's consider the following example of an iteration, where what we are going to do is we're going to say x at n plus 1 is equal to x at n squared. Okay, so we're going to start with some number x0, and we're going to square it, and then we're going to take that number and we're going to square it. That'll be our next number, and then we'll square it, and we'll square it, and we'll square it, and we'll keep squaring it forever. And what we're really interested in is for which choices of x0 does this iteration converge to a finite number? And for which choices of x0 does it blow up to infinity? So we're interested in for which choices of x0, the number that we start this iteration with, where we're just going to square, 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 for which ones does that stay finite? And for which choices does that blow up to infinity? And if you think about that for, oh, I don't know, 30 seconds or a minute, you can come up with the correct answer for this, I'm sure, right? There's nothing particularly tricky about this iteration, but I want to play with this sort of visually. So what we have here is just a little tool that allows for us to select an x0 and then look at what happens to the iteration. So we'll select an x0 and square it, and then square that, and we'll see where we end up going on to start just the real number line. But this is in 2 dimensions because we're going to start thinking about complex numbers here in a moment. But for the time being, let's just think about real numbers. Okay, so right now we have the iteration starting at 0. 0 squared is 0 times 0 is 0 is 0 is 0, right? So we never leave the origin here if we start this iteration at 0. If we move off the origin, this starts to get a little more interesting. So let's say we start that iteration at 1/2. So we're starting this iteration at 1/2. 1/2 times 1/2 is 1/4. 1/4 times 1/4 is 1/16. 1/16 times 1/16 is something much smaller than 1/16, right? Every time we square this number, it gets smaller and smaller and smaller and smaller. And in fact, it's converging to 0. This is converging to a finite number. And we can make this number even bigger. In fact, we can make it any number that we would like that's less than 1. Let's take it all the way up to, say, 0.99. And if you square a number that's less than 1, you end up with a number that's smaller than the number that you squared, right? So if we start at 0.99 and we square that, we end up with a smaller number. You square that number, you end up with a smaller number. Square it again, it gets smaller and smaller and smaller and smaller, and it converges to 0. 1 is a special case. If we're at 1, 1 squared is 1, times 1 is 1, times 1 is 1. So we sit here at 1 forever. So this is also stable in that it does not blow up to infinity. It just happens to be converging to a different finite number. Everything less than 1 was converging to 0. 1 exactly is converging to 1. But we can think about negative numbers too. So let's bring this back to the origin and start thinking about what happens if we start with a negative number. Let's say we start at -1/2. So we're out here at -1/2. Oops, it's taking a little while to catch up. If we start at -1/2, -1/2 times -1/2 is positive 1/4, right? So we start here. The next step of the iteration, we're at positive 1/4. And now we're on exactly the same path of convergence that we were on for the positive numbers, right? And just like the positive numbers, we can take this up all the way to -0.99. And we're still going to converge to 0, right? -0.999 times -0.99 is some positive number with a smaller magnitude. And then we're on the same path of convergence that we were on for positive 0.99. And again, -1's a special case, right? -1 times -1 is 1. And then we sit here on 1 forever, which is also stable. Now, if we step even the tiniest bit above 1, this blows up to infinity. A number greater than 1 squared results in a bigger number than you started with. You square that, it gets bigger and bigger and bigger without bound. So any number greater than 1 blows up to infinity. Any number smaller than -1 also blows up to infinity. These red dots are going bigger and bigger and bigger. So if we wanted to talk about the region of convergence for this iteration, we could paint the real number line. We could paint the real number line between -1 and 1. All of the choices of x0 in this part of the line converge to a finite number. All of the choices for x0 outside of this boundary diverge, explode to infinity. Does that make sense? Okay, so now let's add just a little bit of complication to this. So I'll say the next iteration we'll consider. And it's essentially the same iteration, except that, so let's say, oops. We'll say, let's consider almost the same iteration, except we'll allow for our numbers to be complex. So we'll say z, which we typically use to represent complex numbers at n+1, is equal to z at n, z at n squared. You've all seen complex numbers before, so I'm not going to spend too much time talking about them, but you know, they're just 2D numbers. They're just numbers that we represent on a plane instead of on a line. So we could go back to our visualization here, and let's put everything back at the origin. And complex numbers can have real parts and imaginary parts. Let's consider complex numbers that just have imaginary parts. So let's say that we are starting this iteration up here with some purely imaginary number. So say we are starting at 0.5i, 1/2 I. Yes, what's the path of convergence for this? Well, you will recall that the definition of I, the imaginary number I, is that I squared is -1, right? So if we're at 1/2 I, and our iteration says that we need to square this to get to our next value in our iteration, 1/2 I times 1/2 I is 1/4 I squared. I squared is -1, so that puts us down to -1/4 on the real number line. -1/4 times -1/4 is positive 1/16. And then we're on the same path of convergence that we've seen before, right? And in fact, we could take this all the way up to just below magnitude 1 away from the origin on this imaginary axis. 0.99 I, we go down to -0.99 squared, and then we're squaring a negative number, so we're back on the real axis, and we converge again towards 0. And as before, 1 is a unique case, right? I times I is -1, -1 times -1 is 1, and then we sit here on 1 forever. And we could go down in the negative direction here on the imaginary axis as well. And just like on the real axis, we still converge up to a certain distance away from the origin. So down to say -0.75 I. We're still converging. So it appears as if we can get a distance 1 away from the origin along any of these axes, and we're still going to converge to 0. What if the number that we start with has both real parts and imaginary parts? So we can take a look at the path of convergence for those sorts of numbers. And the path that it takes to the origin is a little bit more spirally and interesting. But as long as the magnitude of the complex number is less than 1, then when we square it, we end up with a new complex number with a magnitude, which is to say a distance from the origin that's smaller than the original number. So if we start out here in the complex plane and we square this number, we land here, closer to the origin. Square that, we land here, closer to the origin. Square it again, square it again, square it again, and we're still converging to 0. So we can talk about for what choices of initial imaginary number do we converge to a finite number, and for what choices does this iteration explode to infinity? And if you play with this for a little while, you can start to build up an intuition for this particular iteration, where it should stand to reason that as long as we stay within the unit circle in the complex plane from the origin, as long as we stay within this unit circle, any choice of initial number within this circle is going to converge. It's going to be a stable iteration. If we dip at all outside of this unit circle, suddenly the whole thing explodes. Does it make sense? So what we're asking is, for what choices of z0, for what choices of complex number, does this iteration of square it, square it, square it, square it, square it converge to a finite number, and for what choices does it diverge to infinity? And for this very simple sort of example, you might be able to solve analytically for this circle and get a sense for what this region of stability looks like and for what its boundary looks like. But suppose that this region of stability were more complicated, right? A strategy that you might use in order to get a sense for what this region of stability looks like is you might do something like the following. You might say, okay, I have some region that I'm interested in, some region of the complex plane that I'm interested in. Maybe I'm interested in numbers with real parts that are between -2 and 1, and imaginary parts between -1 and 1. And I'm going to consider a whole bunch of points within this region. And for each of those points, I'm going to run this iteration that we've just been considering. And I'm going to ask, does that particular point diverge, or does that point converge to a finite number? If it converges to a finite number, I'm going to mark it with an X. If it diverges, I'm not going to mark it with an X. And I'm just going to see which of these points converges under that iteration of square it, square it, square it, square it, and which of these points diverges. So I'm going to run, that's exactly what this little snippet here is doing. But think in your head, when we run this, right, so we're going to evaluate the square it, square it, square it iteration for each of these points. Which of these points do you expect to be marked with a black X, and which points do you expect not to be marked with a black X? Which of these do you expect will converge and which will diverge? And I could have run these beforehand, but I honestly kind of like the suspense that it builds to wait for them to run. It gives you an opportunity to think about this, right? So we're evaluating that iteration on each of these points. And we're seeing which ones diverge and which ones converge. This is taking longer than it did before. I wonder why. What do people think? Based on what we were just playing with up here, what's going to which of these points diverge and which ones converge? Lesson learned here. I'm not going to run the next one in real time. I have this run, this run already. I'm not going to wait for it to run again. Without Zoom open, this took maybe 15 seconds to run. With Zoom open, it seems to take much longer for some reason. People have guesses though? Okay, it's finished. So this should agree with your intuition. Right, so we've run this iteration on every one of these points up here. That is, we've run this iteration, square it, square it, square it, square it, on every one of these test points, and the ones that converge, we marked with an X. The ones that are stable, we mark with an X. The ones that blow up to infinity, we do not mark with an X. And in fact, I kind of made them a little bit transparent to sort of mark them as diverging. And what you can see is that the numbers that are within a distance of 1 from the origin converge, and the ones that are farther than 1 from the origin diverge. A complex number with a magnitude less than 1, when you square that over and over again, it converges to a finite number. A complex number with a magnitude greater than 1, when you square it over and over again, grows without bound. So this is a low resolution approximation of this circle, which describes the boundary for the region of convergence for that iteration. Does that make sense? Okay. So then I want to consider another iteration, very similar to this one, and go through essentially the same exercise. So one more iteration. I want to consider this iteration, but every time we square this number, I also want to add some constant, C. This could be a complex number too, right? And I want to say that Z0 here is equal to 0. And I want to ask the same question that we've been asking, which is, we're fixing Z0 here. We're going to say we're starting at the origin, but then for which choices of this constant that we add in every step of the iteration does this iteration blow up to infinity, and for which choices of this constant does it remain stable? And as before, we can play with this and try to get a sense of it, right? So right now I have Z0 here at the origin, and right now our constant, I also have this set to 0. In fact, let me get rid of this circle because it's just going to confuse things. So we have Z0 here at the origin. We also have our constant here at the origin. And now I want to make our constant non-zero, right? So we're going to start at 0, square it, and add some constant. Let's make this constant, oh, I don't know, 0.1 or so. Okay, we're still stable. We're trying to get a feel for what this region of stability looks like, for which choices of this, as I move this constant around this plane, where can I put it and have this iteration converge to a finite number? And where does it diverge to something infinite? And I'm trying to move this around to get a sense of what this might look like. In the case of the circle, I could move this around and develop an intuition of what that boundary of stability looked like. And I want to see if I can do that with this as well. So we're still stable here. Let's move this out a little bit further. Still stable, not blowing up. Still stable. We're converging to a number that's different than 0, but that's okay. We're still converging to a finite number. Still stable. Oh, we just exploded. Okay, so the point just to the left of this, whatever the shape of this boundary of convergence is, right? Whatever shape we can draw on this plane where the points inside that shape converge and the points outside of that shape diverge, the point just to the left of this one was inside that boundary, and the point just to the right is outside that boundary. But okay, so that's some information. We can explore this plane a little bit more. I want to start moving off the plane. Now you can see this is still diverging. It's taking some different path to infinity, but it's still going to infinity. Oh, that converges. So all I did was rotate this point. So down here we were unstable. Now we're stable. Keep rotating. Still stable. Let's move out a little further from the origin and see what happens. Still stable, taking some really interesting paths to some stable point. Oh, I don't know what's going on there. Maybe that's stable, maybe it's not, who knows? That's unstable. Okay. Let's keep rotating around a little bit. Still stable. Still stable. Move out from the origin a little bit. Okay, we're still stable. Now we're in some sort of starfish pattern. Well, now we're unstable. Really hard to get a sense of what this boundary of stability looks like, right? Just by moving this thing around. You can't really develop the intuition like you could with the circle. It's difficult to tell what exactly the rule is that's going on here. And these paths that they're taking to stability are fascinating and hard to predict also. It's sort of this, they seem almost predictable, but they're also unpredictable. Sometimes they just land in clumps. This is a stable solution, but that stable solution is going to 4 clumps. We move out a little bit further. Now we're in 4 different clumps. Now we're unstable. Keep rotating around. Still unstable. Still unstable. Well, now we're stable again, but now we're in 3 clumps. Now we're unstable again. Now we're stable. really hard to tell what is going on. Put this at 0.7 away from the origin and just rotate around here. And by the way, these trajectories that they take to stability, these sort of interesting patterns, these are called the orbits. So that's stable. That's stable. It's taking a very different pattern. Now we have 1, 2, 3, 4, 5 arms. Now we're spinning the other direction and we have more arms. It's really, this iteration, right, is almost the same as the very simple one that we were just looking at. We're just adding a constant every time and starting at 0. But it has made this shape really difficult to figure out. And in fact, the circle clearly no longer describes the region of stability here, because I can extend this further than 1 unit from the origin, and I'm still stable. So now there are points within this circle that were previously stable that are now unstable. There are points outside the circle that were previously unstable that are now stable. If I rotate this a little bit, and now it's unstable, right? It's so hard to get a sense of what the hell is going on. So in an attempt to try to get a sense for what's going on, we can deploy the same tactic that we used for the previous iteration, right? Where we thought, okay, I want to get a sense for what this region of stability looks like. So I'm just going to populate this area with a whole bunch of test points, and I'm going to run the iteration on each of those test points. And if it converges for that test point, then I'll mark it with an X. If it diverges, I won't mark it with an X. And maybe that'll start to give us a sense for what this region of stability looks like. And by the way, the person that was playing with this was Benoit Mandelbrot. He was doing this at IBM. He was playing with these iterations and playing with these rules. So we're going to consider the same array of test points, okay, which for the iteration that we just considered, when we tested ran the iteration on each of these test points and marked which ones converge versus diverge, we ended up with the circle, which is what we expected. But now we're dealing with this new iteration, right? This one where we're adding the constant, where up here in this little sandbox, we have not been able to get a sense of what this region of convergence looks like. So it's not going to look like this circle. What is it going to look like? And like I said, I won't run this in real time. But think about it, and if any of you have any background in this material, then you know what it's going to look like. But if you don't, try to think about what you think this region of convergence is going to look like. And then when I show it to you, see how well your intuition matches what it actually looks like. I'm going to pause for like 5 seconds and just drink seltzer and let you think about what you think this thing's going to look like. Okay. So this is what it looks like. And you look at this, and you think, what in the hell is going on? And by the way, I've chosen this number of test points because in the first paper that showed a picture of the Mandelbrot set, I'm going to show you the first ever published photo of the Mandelbrot set. And that photo looks like this. So I've attempted to choose the same number of test points that they had available. So Benoit Mandelbrot was at IBM. He was working at a computer. Keep in mind that back then, computers did not have monitors, right? So he would write some code to run these iterations on about this many test points. That code would take a while to run, a long time to run. And then he would send it off to the printer department, because this was in the day where the printer was its own separate department that had its own technicians, because the printer was always having problems. So he would run this code and send it off to print out what this result looked like, right? Each of these test points, he would print out X's for the test points that converged, and he would not print out the test points that didn't converge. And this came back to him. Actually, after a few iterations, this came back to him, because back then, there were lots of printer artifacts. So the printer technicians saw these sorts of things coming out of the printer, and they said, oh, we'll just clean that up for them a little bit, right? Clearly, this is just some sort of printer artifact. This is probably some sort of printer artifact. Let's just white that out, clean it up, and then we'll give it back to Mr. Mandelbrot. So he would get these marked up prints back from the printer department and couldn't understand why. He was like, I'm doing this by hand, and I feel like some of these points that are not getting X's should have X's. So we went to the printer department and they said, oh yeah, well, we're just cleaning it up for you. He said, stop cleaning it up. I want to just see what the printer produces. And this is what it produced. And the first question that he would have asked himself is there some kind of error in my code, right? Because who knows, this is a really unusual shape. And what exactly is this shape? You almost feel like you want this to be a circle, but it's not. There's some gap here. There's some weird bulbs on either side of this gap. It's bizarrely asymmetric, right? There's a bunch of stuff over here that's not on this side. You kind of feel like it should be symmetric, but it's not. And it's very difficult at this resolution to get a sense for what this boundary looks like. Or if this boundary is even continuous, right? Like up here, it seems like maybe there are actually islands of stability or something. You can't tell at this resolution what this boundary looks like. And in order to get a better sense of what that boundary does look like, you need to run this iteration on more test points. That required better computers, right? Because just doing this in the computers of the day takes a really long time, right? So, but in a few years, there would be better computers. And when you run this to a higher degree of resolution, you end up with pictures that look like what I'm about to show you. Which look like this, right? So this is exactly the same iteration, just at higher resolution. Just this array of test points, there's more of them, right? And but as before, the ones that are converging to a finite number after being subjected to this iteration over and over and over again, they are marked black, and the ones that diverge are left white. And you end up with this picture, which almost makes you scratch your head even more than before, right? Because the question is, well, that boundary looks rough. And at least the obvious question, well, how rough? And it would take a few years, and it was actually some folks here at Cornell, folks that are still here at Cornell, that helped figure this out. The answer to the question, how rough is that boundary, is infinitely rough. It's infinitely rough. You can zoom in on that edge, and you will keep finding more edge. You can go down and down and down forever, and you will keep finding more structure. There's an entire universe of structure embedded in the edge of this, right? This has since become one of the most famous images in mathematics, right? And the way that you often see this depicted is, you'll recall up here when we were playing with this toy, some of these points that we picked, it was obvious in a few iterations, oh, that's blowing up to infinity, right? For other ones, they bounce around for a really long time and then they blow up to infinity. So you can sort of get a quantified sense of just how unstable a point is. It turns out that for this Mandelbrot set, it turns out that if the magnitude of the complex number is ever greater than 2, that is to say, if the number is ever further than a distance 2 from the origin, it's never coming back. It's going to blow up. If it's less than 2, it might come back. So you can run this iteration, and instead of just marking a point as stable or unstable, you can do that, but you can also assign a color to the unstable points to tell you how unstable it is. How many iterations did it take for it to get a distance 2 away from the origin? And when you do that, you end up with these sorts of pictures, right? So this is exactly the same picture, but some of those points that are unstable, that we were previously just marking as white, we're indicating how unstable they are. And this is how you end up with these gorgeous images, right? These really, really gorgeous images. And I'm sure you've all sort of seen these videos before, but I mentioned that this boundary is infinitely rough. What that means is, oh boy, is this gonna play? Let's see. If this doesn't play, then all you have to do is Google Mandelbrot zoom and you'll find a gajillion of these videos. But what that means is you can zoom in on the edge of a Mandelbrot set, like what's happening here. And no matter how far in you zoom, let me speed this up a little bit. No matter how far in you zoom, there's still more stuff. So if you have enough patience, and if you build an iterator with sufficient resolution, you can explore the edges of this structure and find structure that no human being has ever seen before. You can explore the Mandelbrot set and you can find things that have never been seen before. So this video is 16 minutes long. You can find videos that are hours long because you can just keep going down and down and down, and you keep finding structure and you keep finding new structure. Structures are different. So it's infinitely complex. And then weird things happen, like we've zoomed down really far and suddenly there's another Mandelbrot set down here. What the hell does that mean? I don't know. But this calls to mind some questions. If there's infinite structure here and it's infinitely deep, could you find your name somewhere? In principle, yeah. But how would you even look? Is there any strategy for looking for that other than just random searches? Anything that's better than just random searches? So it's unbelievably beautiful. It's unbelievably beautiful. It feels like one of these things that's just a gift from the universe, right? It's not clear why this thing exists. It doesn't have to exist, but it does. It's gorgeous. And it's just so addicting to explore it. So I mentioned that, we started out with resolution like this, and people couldn't really start exploring the properties of this set until more sophisticated computers started being built. Computers that we would not call supercomputers today, but back in the late 70s and 80s, they were classified as supercomputers. And Cornell was one of the only places in the nation that had one of these computers. And a professor here that's still in the mathematics department, John Hubbard, was he and a colleague in France, Adrian Dowdy, were some of the first people to really investigate the Mandelbrot set. And in fact, it was Adrian Dowdy who named it the Mandelbrot set. Benoit Mandelbrot did not name it after himself. It was given that name by Dowdy, who was working with Hubbard here at Cornell. And I'm hoping I can elicit some stories from Bruce, because these supercomputers had a staff working with them. So at the time that Hubbard was investigating these things, Bruce was on the staff at the Theory Center and was helping learn some of the early things about this Mandelbrot set. Bruce, can you just like describe basically what that computer was capable of and what you folks were doing with it?
Sure. So the National Supercomputer Centers, there were 5 of them, were established in 1985 because at the time there were no powerful computers in the US except at defense labs, and they weren't available to the research community. So Cornell got one of the sites in collaboration with IBM. IBM provided one of their top-end mainframes that was the first iteration of the Cornell supercomputer, and it had 6 processors. It was a large coarse-grained parallel machine, large meaning several thousand square feet, and could produce about 10 million floating point calculations a second. Now your phone does way better than that, but at the time it was pretty amazing. And the next year they got a vector accelerator that sped the system up a factor of 4 or 5. So at that point, one of Hubbard's students and then employees, Homer Smith, started trying to produce high resolution images so they could understand what this structure looked like. And also because he thought they were pretty. So as soon as we got a new piece of graphics gear, I ran the graphics group for 10 years. As soon as we got a new piece of graphics gear, Homer would come over and beat it to death, getting the maximum possible performance out of it. In 1985, it took probably a few minutes to produce the image that Hunter is sharing right now. The first computer I programmed it on was in 1979, where it took between 2 and 4 hours to do this. It was an Apple II. And what you'll find is on the FPGA that one of the ARM9s will do it in about 1.5 seconds, and the FPGA will do it in, what do you figure, 50 milliseconds.
This image was produced in 50 milliseconds using the FPGA.
So at the time, this was a difficult research calculation, and they would find an interesting area almost by trial and error, zoom on it, and every time they zoomed, like one frame of that video, it'd be another 10 or 15 minutes to get a result. So you couldn't do a very deep search. But what Hubbard, the first main result that Hubbard and Dowdy managed to prove is that this set is connected. There is a boundary, and the points inside the boundary converge, and the points outside the boundary diverge, and that the boundary is arbitrarily complex. Unbelievably slow computers by modern standards. Anything else, Hunter?
I don't think so. I'm including some images here of this whole structure has subsequently been explored quite a lot. As Bruce mentioned, it's an infinite space, right? So in some sense, an infinitely small amount of it has been explored. But some of the higher level areas have been explored enough to have been given names. So the area between this main section here and this, which I believe is called the head, this region in here, if you zoom in on that region, you get these sorts of images. This area of the Mandelbrot set has been given the name Seahorse Valley because these structures here, they look sort of like upside down seahorses. Here's the head, spirally tail. If you zoom in on one of these things, you get more seahorses. And there are other, I'll just show you some other interesting regions of this set. And if you go online, you'll find 1,000 of these. Unbelievably interesting. Unbelievably interesting. And in lab 3, you will be asking for the FPGA to render this set. And I have a picture here of, this is a rendered Mandelbrot set by the FPGA. And furthermore, you'll be able to zoom and pan on that Mandelbrot set up to about 2 to the 10th to 12th-ish. Which means you'll be able to zoom far enough to really explore this space and find really interesting structures. And you can experiment with different colorizations. right? You can color this in different ways and try to try to make it sort of as aesthetically nice as you would like. Let's see, do I have more of these? You get these interesting spiral patterns. What number am I on? 8. Strange sorts of islands. So lab 3 I find to be unbelievably fun and addicting, because once you get it to work, you can actually go explore this space and find really, really interesting things. You guys have questions?
Every almost copy of the Mandelbrot set contained along the boundary is an almost copy. It is distorted in some slight way from the main image. And I don't know if it's been shown or not that there are no repetitions on the edge. But every one of these structures is just slightly different.
And by the way, when you zoom in very far like this, you can see just how sensitive this iteration is to your choice of that constant C, right? These colors represent, if you look at this, I don't know exactly how far zoomed in this picture is. It's 2 to some very large number, but you can see that the points here converge and the points just over here diverge. It's hyper sensitive to your choice of that additive constant C. Makes it very chaotic, right? If you know that some point converges, it does not, along the boundary, it does not give you much information at all, if any information, about whether the point directly adjacent to it, infinitely close to it, also converges. It's extremely sensitive. But it is a picture of a boundary of stability. That's what the Mandelbrot set is. It's a picture of a boundary of a stability for a very simple iteration. And from that extremely simple iteration, it generates something that is infinitely complex, and stunningly beautiful. Okay, that's all I got for today. Folks have questions? If not, I'll see many of you in about 90 minutes, and I'll see no class on Wednesday. So I'll see many of you in 90 minutes, and then I'll see the rest of you on Friday.
Thank you.